Hello, everybody. Thanks for having me a second time at Demuxed. My name is Mario. I'm Bitmovin's technical product lead for the test automation platform and Streamlab. And I thought that testing and QA are a little underrepresented at this conference, even though they are quite important to ship a stable product, also in the video domain. So today I'll tell you a story about how we test our HTML5 JavaScript video player and specifically how we transformed a manual into a fully automated process. Okay, let's start with the basics. You might be familiar with the test pyramid. It's like the food pyramid, only that it tells you how many different kinds of tests you're supposed to write to get a healthy software product. There's lots of different versions around, and they all agree on one thing. On the bottom are the unit tests. They're cheap, fast, and cover isolated pieces of code. And as we go upwards through that pyramid, these tests, they become more expensive, slower, and test increasingly integrated components. Somewhere in between, you'll find, for example, integration tests, and at the top, depending on who you ask, they'll be called system tests, or API tests, or end-to-end tests, or acceptance tests, or functional tests, sometimes UI tests. And this top of the pyramid is what I'll talk about today. And yeah, we all know naming is hard, right? So I won't make a science out of this. And I simply call them player tests. Now, what are the goals of these player tests? Of course, we want to make sure that every feature of the player works correctly on every platform. And that includes detecting bugs and regressions in terms of functionality, but also performance. And those tests, they should represent real use cases and use the player just like our customers use it when they integrate it into their products. So they test the player as a complete product. And a very trivial example test case is, for example, validating that playback works. Such a test would create a player instance, load a stream, start playback, and then somehow assert that it's actually playing. And the root cause why I'm here today is that we basically did this manually when I joined Bitmovin as a software developer 6 years ago. We had a suite of player tests that were kind of scripted, but this still required a lot of manual effort. And we managed our test results in a spreadsheet that looked like this. There were like 26 test cases, and those tests had to be repeated multiple times because the number of test executions basically depends on the number of interdependent features. And then all of those, again, multiply with the number of supported platforms. So the actual complete spreadsheet looked like this. And yeah, that contained more than 1,500 test executions for a suite of only 26 test cases. And that took really a long time, that it basically kept the whole team busy between an afternoon and a week, depending on circumstances. And so we only ever tested release candidates, not individual feature branches. And it was really very bad. So to be honest, every time we did have a player release, I felt a strong desire to go on vacation and skip this tragedy. And yeah, it wasn't only super tedious, it was becoming a real bottleneck in our development process. And it certainly wasn't able to scale with new features or additionally added platforms. So instead of wasting my vacation days, I started working on an alternative solution. And today, we have a fully automated platform that executes about 200,000 tests every single day, spread over 100 real consumer devices. I started out doing this alone. Later, I hired a team of 3 that is now developing it. But in comparison with the test efficiency we had 6 years ago, what do you think how many full-time testers would this need today? It's more than 300. So this allowed us to heavily scale, and it also brought us many additional improvements. And now I'll show you how we did that, starting with test automation. So first step was automating that our tests execute, and for that we need a framework that executes tests and determines results. Of course, I evaluated existing ones, but they were either too heavy or they were difficult to extend with the custom functionality that we needed, which is Mainly, it needs to be very, very lightweight and not put an additional burden on weak devices in terms of CPU and memory. It needs to be aware of its context, so that every test can be conditionally skipped depending on the environment it's running in. For example, depending on the browser or the operating system or device type or available functionality. Because this allows us to run the same test suite on basically every platform and device. For example, on a platform without DRM, the DRM tests are simply skipped. And very important, every test gets automatically a stable test ID assigned that we can use to record the history of the test results. Then, next we made writing tests simpler with a Fluent API. So this is an example of the test case I mentioned earlier. On the left, the traditional implementation, and on the right, abstracted by this API. That's a 90% code reduction and really makes a difference. And yeah, today we have much more than 1,000 test cases written this way. How do we actually execute our tests? So we're not using the typical solution, which is WebDriver. The reason is, in the past, releases were often a little delayed, so we couldn't test the latest browser releases on their release day, and let alone pre-releases. And yeah, today we still support platforms which don't have WebDrivers at all. So instead, I wanted a vendor-independent solution that just works everywhere. And so this became a standalone web application, which we call the test client. And yeah, this goes against typical design patterns because of two disadvantages. First, like every test executes in the same context, so there is the possibility that they could interfere with each other. And if a test manages to crash the process, the whole test runner is gone. But for that, we have guards in place and also mechanisms for crash recovery. The huge advantage, though, is that this application, it loads and executes the tests all by itself, and all it needs is a web environment and navigating to the URL of this test client. Yeah, also it doesn't need any setup. So then there's a server side also in the cloud, which records and stores the test results in real time and also exposes test reports. And in combination, this basically allows us to run test sessions on any device, anywhere in the world, without any setup. So for example, the slides on here are just Google Slides. I could navigate to this URL and then run a test session here. Okay, and now we're collecting large amounts of test results. And there will be failures among them. That's unfortunate, but impossible to avoid. So how do we handle those? What's important to acknowledge here in our case is that flakiness is expected in our setup because we test on real devices and we use real streams from CDNs. So they can't really be considered deterministic. And to distinguish such failures from flakiness from actual unexpected failures, we triage the test results per platform by looking at this history that we are recording. And that's a very simple logic, actually. Once a test succeeds 20 consecutive times on a platform, we consider it a stable test. And when a stable test fails, it's a severe failure that we handle with priority. All right, so now we have an application which can run test suites automatically from start to finish. It generates test reports, it analyzes the results, and we have over 1,000 test cases, but that still needs to be started manually. For example, if we wanted to run tests on a smart TV, it required an engineer to manually acquire this TV, maybe from a remote office or even ordering it, then configuring it, getting a dev machine, installing an SDK, connecting both, building an app, deploying and launching it, which then ultimately runs the tests. So now we get to the trickier part. How can we automate all of this and test on a range of different devices? So automating a device means being able to control it. And what options do we have there? Like the most trivial one is power supply for devices without batteries, cutting power turns off, providing power turns on again. For example, with a smart plug. Then there's physical buttons like the classic power button, but we're not using those. In a network, you can use WAKON to turn on a device. There might be remote command lines, but they are often restricted without routing or jailbreaking. Then there's the classic infrared remote that everybody of you probably use in their living room for the TV. Newer models also use Bluetooth instead. Almost any device has USB ports to connect a keyboard or a game controller, and smart devices usually also expose HTTP or WebSocket APIs, and they are frequently used for remote control apps on your smartphone. Then there's SDK tools from vendors which might simplify certain functionality here. There are some standardized protocols in use. For example, like USB always works the same. But there are a lot of custom protocols, and there's not a lot of official documentation. And to pick adequate interfaces, we follow quite a simple strategy. We use the simplest and most universal interface that's available and close functionality gaps with vendor-specific interfaces. For example, for smart TVs, that means we mainly use infrared. It's an antiquated interface, but it saves us a lot of implementation and maintenance effort, and it allows us to control any of our 60 TVs. Then another interesting topic are third-party services. Why do all that automation ourselves when we can just buy it as a service? That's what we thought in the beginning, but unfortunately it turned out that we were missing features, we had stability issues and hit limitations. So over time, we progressively actually implemented all of this on our own. And ultimately, this even led us to develop our own IoT control hardware, currently for infrared, USB, and camera. And here's a list of the platforms we integrated. Of course, we support all major web browsers on common desktop and mobile operating systems, a range of common smart TV platforms like Samsung, LG, and so forth, streaming sticks, and gaming consoles. And now, the market demands from streaming services to support more and more platforms, which means our player supports more and more platforms, which of course means that we continuously expand this test automation platform. And as mentioned earlier, currently we have over 100 devices, but that includes duplicates for redundancy and parallelization. And what's important here is that we only use real devices. We're not using emulators or simulators or virtualized environments because we noticed they have prohibitive limitations sometimes. They can behave differently. Sometimes they perform poorly, or they even lack functionality, which is specifically important in our domain, like video decoding or hardware acceleration or DRM. And all those integrations or automations that we have, they're basically managed in a distributed system consisting of 3 layers that looks kind of like this. So like the first layer are the controlled units. We call them targets, not devices, because a device can expose multiple targets. For example, a Windows computer is a device, and the browsers on it, like Chrome and Firefox, are the targets. These targets are controlled by agents running in the local networks that actually contain all that automation logic. And then there's a central coordinator somewhere in the cloud which distributes the workload across those targets. And interfaces also with other systems, and that's how we basically integrate the system into our CI workflows, into GitHub to make sure that every player release is now appropriately tested. And those targets and agents, they can be dynamically added and removed from the system, which gives us a lot of flexibility. We can easily scale, but we can also temporarily add devices. For example, I could add my living room TV, run some tests on it, and then remove it again from that system. And these targets, they are addressed by various properties, and that allows us to flexibly issue commands like, for example, run the release test suite on Chrome, Firefox, and Safari across mobile phones, or run some other test suite on low-end WebOS TVs from model years 2016 to 2022 in Vienna, or deploy an app package to a PlayStation 5 and provide me a remote debugger. And speaking of debugging, let's take a quick look at a startup sequence of such a target to see a few more key features. So the first step here is a network configuration. Here we can optionally assign a VPN tunnel to any supported country, which allows us, for example, to circumvent geo-blocking of customer streams. Then sometime later, an application is installed. Typically, that's a web browser, if not pre-installed, like Safari and iOS. But it can actually be any web app or native app. And that means we not only execute tests on our devices, we can basically deploy anything. And then it started. And here we can request a debugger, which is then exposed back to whoever uses this target. So summing up, we started out simply seeking a way to automatically execute our tests. And what we have today is a nice system which can run like any version of any test suite together with any player version on basically any device, and specifically on any of our 100 plus automated devices in parallel, and that's how we reached the 200,000 tests per day, as mentioned. But besides tests, we can start or deploy like any website, web app or native app, conduct investigations and evaluations remotely on these devices, which greatly reduce the barriers for our engineers. And every device is basically available at the press of a button and almost works like a local device. In the outline of this talk, I also mentioned COVID lockdowns. We finished this system shortly before like the first lockdown happened, and we moved to our home offices, and all we really did was add a few cameras. If this had happened a few months earlier, we would have probably been in huge trouble, and it would have been a huge challenge to manage all that hardware and give every engineer access to the devices they would have needed at their homes. And in the meantime, we also have other products like analytics and encoding. They're also tested on this platform. So overall, this has tremendously helped us increase the quality and stability of our products and the efficiency of our development workflows. And today, these player tests, they are treated with the same priority as unit tests. And because we know that our customers are facing similar challenges with testing, we recently put an abstraction layer over everything that I just told you with a simple API and a user-friendly UI, and we called it Streamlab. That's currently in beta, exposes parts of this platform, which allows basically everybody to use our devices and test their streams on it to validate the work across platforms. I invite you to try it out. Just open a free trial account and let me know what you think of it. There's, of course, some economical thoughts behind that, but to me it's important to mention that this is also an ecological decision, because I think it just makes sense to use existing hardware as efficiently as possible instead of everybody like buying their own fleet and managing it. Yeah, so I wish I could have gone into more detail, but unfortunately that's it, and I'll be around for questions if you have any. I know there's people out there who developed similar or even more advanced systems, but I also know there's people struggling with testing, and I hope to those I could give some impulses and show you how much is achievable with some creativity and a few motivated developers. Thank you.